In this example, we have a positive charge that's moving into the screen, so that's away from you as you're looking at it. If you were going to represent the velocity vector, you might put it as an X in a circle with our arrow notation, trying to find the direction of the magnetic field at some point which is directly to the left of the charge. There are two ways to do this. You can use the mathematical equation, think about what the cross product gives you, or you can use the right-hand rule. If you choose to use the cross product method, see that your direction of B will go as the direction of V cross R hat. And that's because our charge is positive. So let's see, what's the direction of V cross R hat? Let's define our coordinate system. I'm going to say that plus X is to the right, plus Y is up. That means plus Z is out of the page towards us. So V is into the page. That's the negative K direction. That's crossed with R hat. Remember, R is from your charge to your point. So then R hat is the unit vector in that same direction. So our R hat vector points to the left. That's in the negative X direction, so that's minus I. Minus times minus gives us a plus, K cross I. This result you might know off the top of your head, or you might know that little triangle, same as what I learned in probably first year physics. So you put I, J, K in a triangle, you point from I to J, from J to K, and K to I. As you go with the arrows around the circle, you get positive answers. If you go around the circle against the arrows, you get a negative answer. So K goes to I in a fashion with the arrows. That means our result is J, and it's going to be positive. So J hat is straight up, that's part answer C. So that's how you can do it with the equation. You can also do it with the right-hand rule. To find the direction of the magnetic field using the right-hand rule, we see that our vector B is given by mu naught over 4 pi q V cross R hat over R squared. So the direction of B, if we have a positive charge, is going to be the same as the direction of V cross R hat. To do our right-hand rule, we point our thumb in the direction of V. That's going to be into the page, so down away from me. Then I have to put my index finger in the direction of R hat. As a reminder, vector R is from my charge to my point. So there's my vector R. Unit vector R hat is a unit vector, so it has length 1, but it points in the same direction as R. So I'm going to put my thumb into the page, my index finger, so I'm twisting a little bit here. My index finger is in the direction of R. My extended middle finger shows my direction of B. That's towards the top of the page. So the direction of my magnetic field at that point is straight up. So that's a good thing. No matter which method we use, we get the same answer. Let's do an example with a negative charge. What if we have a negative charge moving to the right and we'd like to find the electric field at some point below the moving charge? So again, we have two ways. We can use the equation or we can use the right-hand rule. If we're going to use the equation, our magnetic field B depends on our charge and V cross R hat. So to find the direction of our B, our charge is negative, so we got to put in a negative sign here. And then we've got V cross R hat. Our V points to the right. Let's get our coordinate system on here. Plus X to the right, plus Y up, plus Z out of the page. So V is in the X direction, that's I hat. That's going to be crossed with R hat. R hat points down, so that's negative J. Negative times a negative is a positive, I cross J. And you might know that off the top of your head, or you might do your triangle trick and see that I cross J is equal to plus K. So the direction of our magnetic field is in the plus Z direction. That's straight out of the screen, or out of the page, or towards yourself. You can also do it using the right-hand rule. To find the direction of the magnetic field using the right-hand rule here, We know that the direction of the field is going to be v cross r hat. That's for a positive charge. For a negative charge, it's opposite that direction. We have to flip our result or rotate it by 180. So in this problem, our v is to the right. That's my thumb. My r points straight down. And I see that when I extend my middle finger, that goes into the page. So v is to the right, r hat is down. Your extended middle finger is into the page. So if this were a positive charge, the magnetic field would be into the page. This, however, is a negative charge, so I have to rotate my magnetic field. So the answer is out of the page for magnetic field for this one. Okay, I think that's worth popping in a little note there. If Q is negative, B from right-hand rule is flipped. And I suppose if you want to be mathematically more precise, you might say rotated by 180 degrees. Let's do another example, and let's use the hydrogen atom because that's kind of a neat example. Atoms actually have little magnetic fields. They're called magnetic dipole moments, and it's pretty neat, interesting physics. And it happens because atoms have charges, electrons, which are moving around. So those moving charges make fields. So that's kind of interesting. For our example, we'll ask, what is the magnetic field at the center of the atom generated by an electron orbiting the nucleus of a hydrogen atom with a speed of 2200 kilometers per second with a radius of 53 picometers? First thing I'm going to do, because our picture doesn't show us the direction of the electron motion, I'm just going to assume it goes around clockwise. So the velocity at the point shown is going to be a tangent to that circle with the orientation given that it's going around clockwise. Okay, so there's the velocity vector. Trying to find the magnetic field at the center, so our r vector goes from the electron to the proton, and the r hat vector then would be a unit vector in that same direction as r. So there's our r hat. That's good. We've got our vectors shown now. Let's write down our Biot-Savart law. So B is equal to mu naught over 4 pi times the charge Q times V cross r hat divided by r squared. Two ways we can do this. You can do magnitude and then direction with the right-hand rule, or you could do your equations. I think I'll go with magnitude and direction from the right-hand rule. So my magnitude of my magnetic field is mu naught. That's my constant. That value is written there at the bottom of the screen in case you don't have that handy. Divided by 4 pi times the magnitude of the charge on the electron times V times sine theta. That was a result we came up with when we first started discussing the Biot-Savart law, divided by r squared. So let's see what numbers we're going to plug in. The charge on an electron, QE, is equal to minus the fundamental charge, minus 1.6 times 10 to the minus 19 coulombs. And of course, we're putting in the magnitude of the charge because we're finding the magnitude of the field. V is the speed, so that's 2200. It's kilometers per second, so we multiply by 1000 to get to meters per second. Sine theta, theta is the angle between V and r hat. If you look at your picture, you can see that that's 90 degrees. The electron moves around in a circle, so the velocity is tangent to the circle, and the radius then is perpendicular to that, so our angle is 90 degrees. And the radius of the path r is 53 picometers, and a picometer is 10 to the minus 12 meters. Okay, put all that through the calculator, and what we'll get for the magnitude of our B is equal to 12.5 teslas. To get the direction, we'll do our right-hand rule. I won't make a video for this, but you should certainly try it on your own. So V is the direction where you point your thumb. Then you extend your index finger. That goes with your r hat. And then your middle finger gets stuck out. You should see that that pops out of the page. So your middle finger will come out of the page. But remember, your electron is negative, so you have to rotate your magnetic field by 180 degrees. to give a result of into the page, where that answer came from doing the right-hand rule.